What's up, gamers? I want to show you something cool I made. This program is Digital Logic Sim, a demonstration tool made by Sebastian Legg for his series teaching the basics of computing and digital logic. You should check out his videos if you haven't seen them. In this program, you start out with nothing but the AND gate and the NOT gate. You can combine these two into circuits, and then save those circuits to be used in bigger, more complex circuits. This program is very fun, and as soon as I found it, I knew I needed to push it to the limit. So I built this. It's an 8-bit general-purpose computer based on Ben Eater's 8-bit breadboard computer. His videos show the full process of building this computer with real hardware, so you should go watch that series to learn more. So let's dive into how all this works. First off, we've got our clock module, which is very basic. It's just the built-in clock module that comes with Digital Logic Sim, and then some basic logic to give us control over that, give us a manual clock mode, as well as the ability to have this halt signal come in, so we can have a halt instruction at the end of our programs to stop the CPU. Here we've got our RAM. RAM is actually the main way that we program this computer. All we have to do is put it into manual mode. We use these 4 buttons to choose which memory address we're looking at, and the value at that memory address when we're in manual mode is just spat out onto the bus here so that we can see it. And then we can put in our code right here. So right now I want to do a load A 14, so that is 0001 stands for load the value at this memory address into the A register on the ALU, and then 1110 is going to be memory address 14. So now we just hit save, and then you see on the next clock pulse it flipped that bit, we saved that in. Now if we look at the RAM, we've got a bunch going on here. Really, our main 2 components is this 16-byte RAM package and this 4-bit register. Everything else in this circuit just correlates to setting up our inputs and control signals for the manual mode. So these top 2 switch between taking in data from the bus or taking in data from our manual mode inputs right here. And then the bottom one switches between taking in output from our manual mode buttons or taking in input for our memory address register. And then these signals down here, or all this right here, just computes the logic for our control signals to control the RAM when we're in manual mode. But if you ignore all the logic involved in manual mode, our RAM really only has 3 control signals. We've got memory address register in, which will latch the values on the 4 lowest bits on the bus into our memory address register, which our memory address register is fed straight into the RAM package. We've got RAM out, which will output the value at the address in the memory address register on the bus. And we've got RAM in, which will save whatever's on the bus into the memory address that's in the memory address register. And if we go and look at this RAM package, it's also pretty simple. We've got this 2 to 4 converter, which takes our two most significant bits in the address and uses that to select which of these 4 packages we're addressing. And then whichever address we're addressing, it'll take in the 2 lowest significant bits and use that to address a specific byte. And then each byte is just a normal 8-bit register. So technically this is static RAM. Next up, I want to look at the program counter, which is actually pretty simple. The circuitry itself for how it all works is a bit complicated, but what it does is pretty straightforward. It's a 4-bit register with 4 different control signals. If we send this reset control signal, then it resets the value in the register to 0. If we send count enable, it adds 1 to the value in the register. And then we can use input enable to override whatever's in the register with whatever it is getting from the 4 lowest bits on the bus. And then we've got output enable, which outputs its data into the 4 lowest bits on the bus. So what this does is it keeps track of where we are in the program. So when we start the computer, it is going to start at 0. It's going to read whatever instruction is in memory address register 0, and then it's going to increment 1 and read whatever's in 1. And then it's going to keep doing that until our program ends, and we get this halt signal. So that's pretty simple overall. Equally simple is our output module, which literally only has 1 control signal. It just latches whatever is currently on the bus into this 8-bit register. And then we've got 2 7-segment decoders, which take this 8-bit value and display it as a hexadecimal. Here we have the ALU, and our ALU has an A register, a B register, and then a flags register. And you'll see we have quite a few control signals here. We've got signals to store whatever's on the bus into the A register. We can output the A register to the bus. We can store into the B register, and then we can output the B register. Now you'll see both of these registers, in addition to being tied to these buffers for their output, is also tied into this ALU. And this ALU is constantly spitting out A plus B. Or if you turn on this subtract control signal, then it's spitting out A minus B. We can turn on the sum register out control signal in order to get that data, that value, onto the bus. And then we've also got this set flags register, which we'll normally do alongside outputting the value onto the bus. And what that does is we've got a 0 flag, so we take all of the outputs from the ALU, literally just put that into a NOR gate, and then if this output is on, then that means A plus B, or A minus B, is equal to 0. So when we set the flag register, it'll set the 0 flag. And then same thing, our ALU has a carry out, so when we set the flag register, if that carry out is on, then we'll set our carry flag. And these two are used as control signals that allow us to do conditional jumping, which we'll talk about later. Now really the heart of everything here is this instruction unit. It's got 3 parts. We've got our instruction register, which we use to store the current instruction that we're trying to work on. We've got another one of those counters that we're going to count through because each instruction is actually going to take more than 1 clock cycle in order to resolve, because first we have to take in value from the RAM and then store it into the instruction register. Then we have to decode it, and then we have to do something with it. And what does that is this control unit, which takes in our current instruction, as well as what current step we are in that instruction, and it generates all of those control signals that we've been talking about. I think the best way to understand how this all works is to see a program in action. So let's write one. We're going to make a program that takes a value in memory address 14 adds it to the value in memory address 15, and then outputs that to our 7-segment hex displays. So let's do that. We're going to start by putting it in manual mode, and then all of our programs are going to start at memory address 0. And first we need to do the load A command, which is going to take the value in a memory address and store that value in the A register in our ALU. So for load A, that command is 0001, and then we want to load in the value of memory address 14, so 1110. So we can save that. And now let's go to our next memory address. We want to load the value at memory address 15 into the B register. So the command for load B is 0011, and then we do 15. Save that, and then we can go to our next memory address, and we want to add those two together. So our add command is 0101. Whatever's in the lower 4 bits doesn't really matter. And what this is going to do is it's going to add A and B, and then it's going to save the result of that addition back into the A register. So we can save that, go to our next memory address, and now we want to output. So the command for output is 0111, and this is going to take the value in the A register and send it to our output register. So we can save that, and then finally, we just want our program to halt. Now, we want to go and make sure we remember to save our data. So let's go to memory address 14. I'm going to save a 9. And then in memory address 15, I am going to save a 3. So now our program is going to add 9 and 3. Hopefully, if all goes well, then we should get a C on this display, because C is 12 in hexadecimal. So I'm going to put it in manual clock mode so that we can step through this one at a time. And before we start, I want to point out that our manual mode doesn't just go into our RAM, it's also going into the reset on our program counter, as well as into the reset on our instruction register, into this counter. So we're always going to be starting at 0. Let's see what it does. So we take off manual mode, and right off the bat, we're already doing stuff. Let's look at this. So our counter here is at 0. And when this counter is at 0, then this control unit is always, no matter what data it's getting in, it is going to do program counter out, memory address register in. So remember I said we always start at 0. That's because our program counter is currently reset to 0, and then we're putting that into our memory address register. So we're going to be looking at what is in the 0th address. So we can clock pulse. Some more stuff is happening. And you'll see our control unit is actually putting out 3 control signals. It is outputting the value of our RAM at that memory address we just set. It's also got this internal control signal that is being used to set our instruction register. And then it is also sending a control signal to increment our program counter. And that is always what it does when this is on the 2nd step. So now we clock pulse again. Now this is on its 3rd step, and we've got our instruction saved into our register, so now we can decode it. So when this sees it's on the 3rd step, and this instruction is 0001 or load A, then it knows it needs to take the value that it just took in this 14, and it needs to put that in the memory address register. So we've got another internal control signal, instruction register out, and then we're doing memory address register in. So we clock pulse again, and now on this step what it's doing is it's outputting the value of RAM, and it is doing a register in. So we just, when we clock pulse, we're going to latch the value being output by the RAM into the A register. Clock pulse again. Now it looks like it's not doing anything. That's because we just finished the instruction. So our control unit sends this end operation control signal that's going to reset this counter. So that way we don't have to wait for the counter to overflow, but we're also able to have instructions that take more than the few clock cycles that that load A instruction took. So now, if we clock pulse, this has been reset. So again, when this is 0, it always does memory address register in, program counter out. So now we get the next value in RAM, and then we're again outputting that value into our instruction register and incrementing our program counter. And now we've got that latched into our register. So now you can see 0011, that's our load B command. And then just like the load A command on this step, we're outputting the value from the instruction register, that memory address, into the memory address register. And then we're outputting the data at that memory address, and this time we're doing B register in. Clock pulse again. We've got another end operation. Now we're on to our next one. So then we go through our fetch cycle. So program counter out, memory address register in, and then we're taking that into our instruction register. And now we've got our add command. So again, our add command is 0101. And on this step, what it's going to do is it is outputting the value from the sum register, and then it's going to latch that back in the A register, and also set our flags register so that we would know later if this ended up being a 0 or having a carry. So we can clock pulse. Again, end instruction, that's the end of our add command. Now let's load in our next instruction, which is that output command. And for this, we're just doing A register out, output register in, and hopefully when we latch this, we see a C, which is correct. And then if we just pulse this a few more times, eventually we load that halt command, and now our clock won't pulse anymore, except in manual mode it will, because manual clock mode overrides that. But there you go. That is an overview of how this CPU is able to execute instructions. Now, if we wanted to be a little fancy, we could actually update this. So let's go into manual mode again. And let's see, where were we? So this is our output command, and then this is our halt command. But instead of doing a halt, if we wanted to just keep adding numbers, we could skip straight back to our add command, which was, which since add constantly saves the value back into the A register, it makes doing this really easy. So our command for jump is 1100. And then we need to specify the memory address that we want to jump to. So that would be, it's the one where we add, which I think is this. Yeah. So we want to jump to memory address 2. let's see if this works. And then actually, just to make this a little more fun, I'm going to change these. So I'm going to make this start out as 0, and then I'm going to add 3 every time. Take it out of manual mode, and it should start running that program. And then to speed it up, I'm going to turn on this boost pin, just to speed up our clock. And then we see 3, 6, 9, see? And yeah, so it looks like this works. 12, 15. Perfect. So that is a program with looping. Now, finally, I've got one last thing I want to show you, which is this is not just a glorified adder. Well, this ALU is a glorified adder because it doesn't actually do any logic operations, it just adds. I will make a real ALU in a later video. But this is actually a general purpose computer that's able to do a lot of stuff. It's very limited because we only have 16 memory addresses, but it turns out with 16 memory addresses and our commands to jump when the carry flag or the 0 flag are set allows us to create some fairly complex programs, including a program that multiplies 2 numbers. Now, this program takes quite a while to load in, so I'm going to speed this bit up, but let me do that real quick. This multiplication program takes up all 16 bytes of our RAM, but the way it works is actually pretty simple. A times B is really just B plus B plus B A times. So all we do is we have A at memory address 13, B at memory address 14, and then at memory address 15 we have a running total that we start at 0. So we add B to our running total, and then we subtract 1 from A. And then if A is not 0, so there's still more of A remaining, we just keep going. Add B to the running total, subtract 1 from A. Add B from the running total, subtract 1 from A. And then every time we do that, we're checking if that A minus 1 is equal to 0. Once it is equal to 0, we know that we're done, so we can output the result and halt the program. So you see it's counting up 8 times every single time, and then when it finishes, we get 30, which is 48 in hexadecimal. 6 times 8. So there we go. I hope you've all enjoyed that demonstration of this simple 8-bit computer that I've built. Next time, I'm going to be actually doing some upgrades to this computer. I really want to see how far I can push this program. And then, in a few videos, I'll start a series where I actually rebuild this computer from scratch, showing you every single step. So you can build it yourself and tinker with it if you'd like. So, if you're interested in that, subscribe. And I'll see y'all gamers later. Peace out.